if we are having n degree polynomial. Suppose in trapezoidal rule we are assuming 1 degree polynomial, then error term is what? That is containing second derivative. In Simpson 1/3 rule we are having third degree polynomial, but their error term is what? That is containing fourth derivative of the function. So Newton-Cotes formula is exact when approximating the integral of any polynomial of degree less than or equal to n. So if we talk about the Simpson 1/3 rule where we are using third degree polynomial, error term is containing fourth derivative. That means what? If we are using polynomial up to the degree 3, then error will be 0. So in Newton-Cotes formula or the Newton-Cotes formula gives exact value whenever we are using function as a polynomial of degree n, otherwise we'll get error in the formula, in the solution of the integration. Okay, next is limitation of Newton-Cotes formula. What is limitation? In Newton-Cotes formula, we use the value of the function at its equally spaced points. So we use values of the function at equally spaced points. Okay, this restriction is convenient when the formula are combined to form the composite rule but it can significantly decrease the accuracy of the approximation. What does it mean? Like in Newton-Cotes formula, it is the restriction that we have to use equally spaced points because all the subintervals should be equal in length. But whenever we are using composite rule, then it is okay. But it can decrease the accuracy of the approximation. Why? Because whenever we are dividing the interval into small intervals and the h is going to be very, very small. In that case, we'll get round off error so that the accuracy of the solution will decrease. Okay, next is, so that's why what we are doing, we are going to introduce next method that is called Gaussian Quadrature. In this method, we are not choosing equally spaced points. In this method, we choose the best point. Here we choose the best point for evaluation rather than equal spaced point or equally spaced point. So in Gauss Quadrature formula, we have to choose equally spaced point. But in Gaussian Quadrature, we are not checking the equally spaced point. We'll try to find out best point so that we'll get better accuracy. Okay. For this reason, this Gaussian quadrature formula is more accurate. Suppose the integration is from a to b fx dx is equivalent to summation lambda I fxi, I equal to 1 to n if both xi and lambda are unknown, then where lambda and xi, both xi and lambda are unknown, then method is called Gauss quadrature. Gauss quadrature. So this integration, if this lambda and xi are not known, then we'll say it is Gauss quadrature method. In Newton-Cotes formula, these I is what that xi point are what? Those are the nodes that divide the whole interval into equal subintervals. Okay, and lambda I are what? Lambda I are the weight that we compute with the help of Lagrange polynomial or by any other interpolating polynomial. But in this lecture series, we have discussed only the Lagrange interpolating polynomial. Okay. So the coefficients, lambda is and xi are restricted only by the fact that they must lie in the interval AB. This gives us 2n unknowns to choose. 2n unknowns to choose. We can obtain these unknowns by making the method exact for the class of polynomials of degree at most 2n minus 1, which gives 2n equations in these 2n unknowns. That means what? These coefficients lambda and xi are restricted only by the fact that they must lie in the interval AB. Okay. This gives us 2n unknown to choose, because if we are talking about lambda and xi. So how many unknowns are here? There are 2n, because lambda is what? Lambda 1, lambda 2, lambda, and xi is what? Where I we can take as 1, 2, 3 up to 1. So there are 2n terms are unknown. So we can how we can obtain these unknowns? By making the method exact for the class of polynomial of degree at most 2n minus 1. Okay, by the same procedure as we have discussed in the preceding part. So which gives us 2n equation in these 2n unknowns. Okay, how to do that? Let us explain it. So let us explain the method, then we'll come to this point again. Okay, so Gauss Legendre integral method. integral method. The Gauss Quadrature formula will derive from here. That is, so the formula are derived. The Gauss Quadrature formulas are derived for the interval. So we are not having only one formula. We are having different kind of formula that we'll discuss later on. The formulas are derived for the interval -1 to 1 and any interval a to b can be transformed to -1 to 1 by using the transformation x equal to ct plus d, which gives x equal to a, then ct plus d at x equal to a, then we are having ct plus d. T is what? That is 1. And the point x equal to b is transformed at t equal to -1. So that's where the value, this is 1 and b as, this is -1. This is +1. Okay, b as t plus 1 plus 2. Compute the value of c and d from here in term of a and b. So this implies that minus c plus d equal to a and c plus d equal to b. So the value of d is coming out to be a plus b. So d is a plus b upon 2 and c is b minus a upon 2. So just the transformation we are getting here, that is what? b minus a upon 2 into t plus a plus b upon 2. So using this transformation, any interval a to b is converted into the interval -1 to 1. Okay. So now we'll derive 1 point formula. So the restriction in Gauss Quadrature formula is what? We have to take interval from -1 to 1. Okay. So 1 point formula is what? That we are taking n equal to 1. As in Newton-Cotes formula, we took n equal to 1 degree polynomial. So this formula will be what? That will be -1 to 1 f of x dx is equal to lambda 0 f of x0. Okay. In this formula, we are putting I equal to 1. Okay. So I equal to 1, we are getting only lambda. Okay, it is I equal to 0 to 1. Okay, we are writing here as a to b -1 to 1 fx dx as summation I equal to 0 to n lambda I f of x. Okay, so we are taking I equal to 0, only this. That we can make change here. Let us take I equal to 1 according to the previous formula. This is I equal to 1 to 1. So I should write here, this is lambda 1 fx1. Okay. Now lambda 1 fx1. So fx will choose as a polynomial. Fx is a polynomial of degree 1 or less. So it will take the value of fx as constant. So what we'll get here? Fx constant, let us suppose fx equal to 1. So what we'll get here? Dx minus 1 to 1, and value is what? Lambda 1. Lambda 1 and fx1. The value of it is coming out to be what? It is the value as 1. Now we are taking fx is a 1 degree polynomial, that is x equal to 1. So what we are getting here? This is equation number 1, suppose. And from here we are getting x dx minus 1 to 1 equal to lambda 1 f of x. It will be what? F of x1. That is lambda 1 x1. Now solving these two equations. So what is the integration of minus 1 to 1 dx? It is coming out to be what? It will be 0. Lambda 1 x1, the value of lambda 1, sorry, not x1, it is lambda 1. From here we see it is lambda 1 into 1 from the equation 1. So lambda 1 is coming out to be minus 1 to 1, it is coming out to be 2. So the value of lambda 1 is 2. Now the integration minus 1 to 1 x dx equal to x square upon 2. The integration limit minus 1 to 1, it is coming out to be 0, and the value as lambda 1 f of x1. F of x1 is what? Lambda 1 x1. Lambda 1 is 2, then the value of x1 is coming out to be 0. This implies x1 is 0. So the formula minus 1 to 1 fx dx is coming out to be 2. The value of x1 is what? 0. So f of 0. So this is the formula we derived. This is called 1-point formula. Okay, similarly we can derive 2-point formula. 2-point formula. Two-point formula, n equal to 2. So minus 1 to 1 fx dx can be written as lambda 1 f of x1 plus lambda 2 f of x2. Okay, so fx, here we are taking n equal to 0, that means fx is a polynomial of degree less than or equal to 2. Since we are having here 4 unknowns, lambda 1 x1, lambda 2 fx2. So here we have to assume, in order to make the method exact, we have to choose, in order to make the method exact, what we have to do, we have to choose the value of fx as 1, x, x square, x cube. It is only possible whenever we will take 4 values of fx, that is starting from 1 to x cube. Otherwise we cannot compute the value of lambda is xi, because 4 unknowns, so 4 equations we require. So that's why whenever we are taking fx equal to 1 here, so what we are getting here, that is fx equal to 1, we are having here lambda 0 plus lambda 1. That is minus 1 to 1 dx, it is equal to 2, equal to lambda 1 plus lambda 2. Fx equal to x, we are getting, this is equation number 1, suppose. For this case, fx equal to x minus 1 to 1 x dx, the integration of x is coming out to be 0, this is lambda 1, and when fx equal to x, and the value of x1, it will become what? x1 plus lambda 2 x2. Now we are taking the case fx equal to x square, so integration from minus 1 to 1 x square dx is coming out to be x cube upon 3. So the integration limit minus 1 to 1, it is 2 upon 3, equal to lambda 1 x1 square lambda 2 x2 square. This is the equation number 2, this is the equation number 3. Now we will take the case fx equal to x square. In this case, x square dx minus 1 to 1, it is coming out to be what? Sorry, x square we have already taken, now x cube. Okay, This is coming out to be 0, lambda 1 x1 cube, lambda 2 x2 cube. This is the equation number 4. After solving ring 1, 2, after solving system of equation 1 to 4, we are getting the value of lambda 1 and x1 as lambda 1 and lambda 2 is coming out to be 1, and the value of x0 is coming out to be plus minus 1 upon root 3 x1, sorry. The value of x1 plus minus 1 by root 3 and x2 minus plus 1 by root 3. The formula is coming out to be minus 1 to 1 fx dx as formula is coming out to be minus 1 to 1 fx dx equal to lambda 1 fx1 plus lambda 2 fx2. So the value of x1 and x2 will put here. So lambda 1 is what? 1 f of 1 by root 3. If it is positive, then value of lambda 2 f of minus 1 by root 3. So this is the 2-point formula. 2-point formula. Third, we'll write 3-point formula. Three-point formula, that is minus 1 to 1 fx dx lambda 1 fx1 lambda 2 fx2 lambda 3 fx3. We'll derive this formula for the value of fx as 1 x square x cube x4 x5. So this is a formula for a polynomial of degree up to 5. Okay, so I am writing directly formula. Derive it by yourself. Derive it by yourself. I am writing directly the formulas from the values of lambda and fxi. Minus 1 to 1 fx dx is coming out to be 5 by 9 f of 3 upon 5 plus 8 upon 9 f of 0 plus 5 upon 9 f of minus 3 upon 5. So this is the 3-point formula. This is 3-point formula. Now let's do an example. Approximate the integral 0 to pi by 4 cos square x dx using Gauss Quadrature 1, 2 and 3-point formula. Also compare with exact result. Also compare with exact result. Okay. Solution. To apply Gauss Quadrature formula, interval is what? 0 to pi by 4. This is your interval a to a. And convert this interval from minus 1 to 1. Then only the Gauss Quadrature formula can apply. So x equal to what? B minus a upon 2 c plus b plus a upon 2. A is 0, b is pi by 4. So what we are getting here? Pi by 4, pi by 8 c plus pi by 8. So this is your, so dx will be what in this case? Pi by 8 dt. Okay, and the value of x is this. So what we are getting here? Minus 1 to 1 cos square pi by 8 t plus 1 dt. And the value of pi by cos square x dx from 0 to pi by 2 is converted into the dt form. So one point formula, is what? That is minus 1 to 1 fx dx equal to lambda 0 f of 0. Lambda 1 f1, lambda 1, okay, or we are getting the formula lambda, that is 2 of f0. Okay, so this is the one point formula that we derived. Lambda 1 we calculated. So it is minus 1 to 1. Function is what? Cos square t plus 1 pi upon 8 dt. It is coming out to be pi by 8. 2 into the value of cos square t is 0. So it is coming out to be cos square pi by 8. Value is 0.3927. Okay, so 2-point formula. 2-point formula, we are getting value here. Cos square t plus 1 upon 8 pi. It is the formula is what? F of, this is your f of t, f of 1 by root 3 plus f of minus 1 by root 3. So the value is coming out to be 0.6423. 3-point formula. Okay. 3-point formula. The value is coming out to be 0.6425. Okay, so we discuss about this formula in 1-point formula. In 1-point formula, we have taken 1-degree polynomial. We have taken 1-degree polynomial for deriving the formula. So error in this case will be what? The second derivative in this case involved in the error. So error will be what? That will be when the function is error will contain second derivative of the function. Okay, as in Newton-Cotes formula. Just keep remember, this formula is equivalent to the trapezoidal rule. So the same error or same accuracy we are getting, same accuracy. This simple formula 2f0, it is very easy to apply. So same accuracy we received. Accuracy. Trapezoidal. Trapezoidal rule is comparatively difficult to is comparatively complex, but 1-point formula is very simple to apply. So we are getting same accuracy as trapezoidal rule. By 2-point formula, we are getting is accurate as Simpson 1/3, because this formula is exact whenever we are choosing the function value from 1x, x square, x square. So this formula is exact up to a polynomial of degree 3. Simpson 1/3 is also true for also exact for a polynomial of degree 3. And this formula, 3-point formula, 3 point formula is exact up to a polynomial of degree 5. So these formula are simple to apply and give better accuracy than the Newton-Cotes formula. So they are much and more used than the Gauss Quadrature, the Newton-Cotes formula. So this topic is over here. This was the last topic of the numerical integration formula, numerical integration. Okay. In the next class, we will discuss about the new topic, that is the system of linear equations. Thank you.